All right, going to be beginning our discussion of Chapter 11, which is solutions and colloids. All right, so we're going to go ahead and try to define what a solution is. All right, so, and talk about the thermodynamics of it. Let's look at two gases that we could put into a container that are separated by a barrier. And on the right side, I'm putting neon gas, and then on the left side, I'm putting argon gas. All right, and while that barrier is in place, we would expect the argon and neon particles to just bounce around in their own containers. And it should be no surprise if we go ahead and remove the barrier. That the argon particles would spread out and the neon particles would also spread out. And if we left it long enough, we would have a uniform mixture that we would call a solution of argon and neon. All right, so if we were to sample any portion of that container, it would be the same no matter where we grabbed it. All right, so that's the idea of a solution. It's a uniform mixture of solute, all right, in a solvent. All right, so what we typically would say is a solution is uniform. All right, and we're not going to get into the formal thermodynamic definition of something called entropy. All right, we'll save that for later, but we're going to go ahead and loosely define this as the magnitude of disorder. In a system. So when we look at the scenario above, the case on the left would be more ordered, correct? I mean, you have argon on one side, neon on the other side. All right, and that's because that barrier is in place. But when we remove that barrier, we get a mixture, and it's much more disordered. All right, the neon and the argon are all over the place. All right, so what's happening here is this mixing of substances is favored entropically. Okay, so we like to see substances mixing, all right, from an entropy standpoint, all right. So this happens spontaneously, so this must be a favorable process from a thermodynamic sense, and that thermodynamic driving factor is something called entropy, all right. So do all substances mix then? And the answer is no, all right. So before we move on, we're going to take a look at Gibbs free energy. Which is defined by this equation. All right, so over here we have change in free energy. All right, and here we have the change in enthalpy. T, of course, is temperature. In absolute temperature, by the way, so it's in Kelvin, so the temperature can never be zero. And the delta S is the change in entropy. All right. So, as we'll discuss, we'll discuss later in our discussion of thermodynamics, any process that gives delta G a negative sign is a spontaneous process at that temperature. All right, and what spontaneous means is this is going to happen, if you will. The process will occur or happen without an outside agency. All right, and what I mean by outside agency, all right, you leave your bicycle out in the rain, for long enough, it's going to rust. All right, that is a spontaneous process. Okay, so the oxidation of iron, for example, is a spontaneous process. It happens without any outside agency. All you need is iron contacting oxygen, and it happens. All right. However, the reverse, taking iron oxide and splitting it to iron and oxygen gas, that is something we call a non-spontaneous process, and that takes an outside agency, all right, in order to drive that reaction in reverse. Okay, so when we looked at the argon and the neon mixing spontaneously, it must have given us a delta G sign of negative. So let's go back to this equation. And let's just ignore enthalpy for a second. So we're just going to kind of remove it from the equation. So how do we get a negative delta G value here? All right, we already have a negative sign here. Temperature, since we're dealing on the absolute scale, must always be greater than 0, so it's always positive. So what that means is an entropically favored process is going to be a positive sign. So delta S positive is an increase in disorder. And that will provide a delta G negative value unless delta H messes with it. And we'll talk about that here in a second. So when we look at processes that are spontaneous, we like to see delta S as positive. All right, so things in the universe that tend towards disorder, all right, are highly favorable, okay? And that is one of the laws of thermodynamics in a nutshell that we'll talk about much later, all right? Now, let's consider how enthalpy plays in, all right? So we go here, and again, if we want delta G to be negative, and we're only looking at enthalpy, let's just ignore the entire thermal and entropic portion of the equation. Well, if you want delta G to be negative, delta H being negative would be a good thing, all right? So delta H negative is exothermic, all right? So processes that are exothermic, all right, tend to make delta G becoming negative much easier, all right? But that doesn't mean that endothermic processes can't happen, all right? So we'll get into this more when we discuss thermodynamics, all right? How we can affect delta G by looking at the interplay between delta H and delta S, right? But what we just need to consider is that right now we're just talking about the thermodynamics of making solutions, all right? So let's talk about that. So what has to happen when you dissolve something into a solution? So let's just jump back into, let's taking some kind of solute and put it into water, okay? So our solute today is going to be this red guy here. I mean, you can pretend it's sodium chloride, all right, for all we need to know, all right? So what has to happen for this crystal, all right, of sodium chloride, if you will, to actually go into solution? So think about this. If you're sitting at home, you've got a piece, or a salt crystal. How are you going to get it to dissolve into water? All right. Well, you put it into the water, obviously. But what is honestly going to happen? Well, this is going to be the first step. All right. The first step is that the solute particles actually have to break apart. All right, so what we're going to do is we're going to call this the separation of solute particles. All right, I would agree that delta S for this process is going to be positive. All right, how do I know that? Remember, it's entropy, and that's the amount of disorder. So has this become more ordered or more disordered? And in this case, it is less ordered, right, because the compound now has free space between the particles, so you have less order here, okay? But what about delta H? Okay, the enthalpy. And how do you figure this out, right? Entropy is pretty easy. You just look if it is less random or more random. All right, delta H, you have to kind of think about the energy required, all right? So remember, what's holding these guys together in the crystal lattice? Those nice electrostatic interactions like the Na pluses and the Cl minuses, right? Those charges are glued together, all right? Now all of a sudden you've pulled them apart and you have these charges, all right, that have developed, like a plus and a minus, a plus and a minus. So that required energy. And when we have to put energy into a system, that's a positive sign. So we are endo, okay? This is endothermic. Okay, now, is this going to be a spontaneous process? All right, well, it really depends on how the interplay between delta H and delta S go. But remember, we're going to be looking at this as an entire sequence of events. All right, how do we get our solid sodium chloride into a solution in water? Okay, so right now, this first step, this separation of solute particles, this is requiring energy at this point. All right, so let's see what the second step is going to be. All right. The second step is going to be the accommodation of solute particles into solvent. All right. So we have our solute particles that have done their first step. They've broken up. All right. However, now we need to take, we're pretending our solvent is water here. Right. So we have 3 water molecules, if you will, here, and they are doing what? Hydrogen bonding to each other. All right. So they're nice and happy, and they are hydrogen bonding. Now, to accommodate these solute particles, now what we're going to have to do is have water break up with other water molecules. And I'm going to go ahead and color these particles in so they don't look like oxygens. All right. So the water is going to have to break its hydrogen bonds and then go and make coordinations to these charged particles. All right, so remember that oxygen has this delta minus here, hydrogen has the delta plus, oxygen has the delta minus, all right? So it can coordinate to these ions through the ion dipole force. All right, so if this was like, Na plus here, this would be Cl minus, and this would be Na plus. All right, so you've broken hydrogen bonding, right, in the solvent. So this is going to require energy. We don't like breaking hydrogen bonding. So our delta H here for step 2 is also going to be positive, all right? So far we've got 2 positive processes via enthalpy. First was the separation of the solute particles. That required energy. Next was the accommodation of the solute particles into the solvent. That's going to require energy, all right? However, our third and final one is going to really help us out. All right, the solvent solute intermolecular force is established. All All right. And the way that works is if we look at a water molecule, remember it has its delta minus here, it can coordinate to a sodium ion. All right. And in fact, several water molecules can do this. And depending on the metal, you can have a variety or a different number of waters coordinating to it. So we're just kind of getting the point here. And water can coordinate there to chlorine via the hydrogen, which is delta positive. All right. So this intermolecular force here is called the ion dipole force. Now, in our previous discussion of intermolecular forces, we only discussed what's called van der Waals forces. All right. Those, for our purposes, were the dispersion force, the dipole-dipole force, and hydrogen bonding. This is not a van der Waals force. This is called the ion dipole force, and this is stronger than hydrogen bonding. So what we've essentially done going from number 2 to number 3 is we've traded hydrogen bonding, which until about 38 seconds ago was advertised as the strongest intermolecular force. All right. We've actually upgraded our intermolecular force to a much stronger one called the ion dipole force. So this is what makes water such an amazing solvent for ionic compounds, is that it can establish this ion dipole force. All right. So when we put them all together, we're going to call this delta H of solution is equal to delta H of the solute breaking up. So this was step 1, and this was endothermic. So I'm going to give it a positive sign. And we're going to go ahead and add the other process, which was number 2, where delta H of the solvent accommodates the particles. This was step 2, and it was also exothermic. All right. And finally, we get delta H of mixing, where the ion dipole force was established, and this was exothermic. All right, because what we ended up doing was trading hydrogen bonding for ion dipole. All right, so what's going to happen is if 3 dominates, in magnitude, we have an exothermic negative delta H of solution. I'm going to abbreviate SOLN, and that is good for a spontaneous process. All right. So how do you guarantee getting a spontaneous process? You get a strong delta H of mixing, and you're guaranteed a spontaneous process because the dissolution is already favored via entropy. All right. Okay. So that's our discussion on the thermodynamics of making solutions. Now I want to get a little more general and talk about the different types of solutions that we're going to see. The one that most of us have experience with is something called an unsaturated solution. All right, this is a solution that can accommodate more solute. All right, to kind of draw a cartoon of what this would be, you have pure water here. You add a little bit of sodium chloride, which would be a salt, and you get a solution. All right. Well, you wouldn't actually see those particles. So let me get rid of that picture. So this would be H2O as your solvent and NaCl as your solute. And if it is unsaturated, you can add more sodium chloride and you maintain a solution. All right. On the other end is something called a saturated solution. And now this is a solution where if you add more solute, it will not dissolve. All right. So what we could do here is we'd have a picture of H2O as our solvent, NaCl is our solute. All right. And if it were a unsaturated solution, it would be nice and homogeneous. You wouldn't see anything. It would just be crystal clear water. All right. And if I try to add in more sodium chloride, then I would see H2O solvent. I would have sodium chloride solute and excess solid NaCl floating around or sitting at the bottom. It doesn't have to be floating, but you get the idea. All right, so there's the definition of a saturated solution. Okay, and you can get super precise and find the exact point where you have a saturated solution that looks like an unsaturated solution, but in all honesty, a saturated solution is going to be one that looks like this. All right, it has the excess solid particles floating around in it. All right. Now, something that's quite weird and neato, actually, is something called a super saturated solution. Now, don't get confused here. It doesn't mean it's like really, really, really saturated. It's what they call above saturation is what it literally translates into. All right, so what we say here is this is where you kind of pull a trick. You add more solute than is allowed, and you make a metastable solution. Now, how in the world do you pull this off? All right, the easiest way to do this is if you take a saturated solution, an abbreviation for saturated is SAT''D. You'll see that quite often in laboratories. So this is a saturated solution. And again, saturated solution, you've got the liquid, you've got the solute in solution, and then you've got the excess solid particles. And we're going to say this is at room temp. Now what you can do is you can add heat to this guy. And the symbol for heat is often the symbol delta. All right. So as you elevate the temperature, almost all substances increase their solubility. All right. Some don't, but most do. All right. So you increase the solubility. And when I say increase the solubility, you're allowed to now put more solute into the solvent. All right. So all of a sudden, at elevated temperature, you have a unsaturated solution at elevated temp. all right? If you are very careful and you cool slowly, you can have a supersaturated solution at room temp. All right? But you have to be very, very careful, because if you shock this system, all right, you add some sort of shock. I'm not talking about electrical shock, even though that could qualify, I guess. A shock could be just tapping the glass, or vibrating it, or dropping in a nucleation point. Something like a tip of a paper clip, or even a coin, something like that. If you were to drop into the solution, we call this crashing back to a saturated solution. All right, so it'll crash back. So what's the point of this, right? Well, it's pretty neat, because in the case of, hand warmers, all right, you can have a super saturated solution in the bag, and then you can snap that little metal thing in there, and that's the shock, and it'll crash back to a saturated solution. During that crash, you can have heat released. Thus, your hand warmer, all right? Also, this is a way to recrystallize materials into their pure form. So those of you that are moving on to organic chemistry, you'll do this quite often, all right? You can take a supersaturated solution of, let's say, benzoic acid, for example. It's just some solid that I was thinking of off the top of my head. You can shock the system, and you'll crash out very highly pure crystalline benzoic acid, all right? And then you can filter that, and it's used as a purification technique, all right? So those are our type of solutions that I'm talking about. And then in the homework, I'll post a video of how some of these supersaturated shock solutions look. It makes some beautiful crystals, to be quite honest. All right. Okay, another type of solution I guess we could have is a gas dissolved in a liquid. All right, so here we're talking about gas as our solute and liquid as our solvent. Now, things are a little bit different here, all right? So we talked just a few minutes ago about how elevating a temperature of a solvent can increase its increase the solubility of a solute in it. All right, that's not the case in gases. All right, let's go ahead and state what I'm talking about here. Gases are less soluble in liquids at higher temperatures. This is quite frankly the opposite of what we see when we take a solid and try to dissolve it into a liquid, all right? Why is that? All right, well, if you have a gas in a liquid, right, remember gases are always trying to escape, all right? They can escape much more easily when they are given more thermal energy. So if you cool the solvent down, you're making it harder for the gas to escape, all right? So if you're thinking about escaping, well, gases are more soluble in liquids at higher pressures. All right, why is that? Well, if you press down or increase the atmospheric pressure above the liquid solvent, you're making it harder for the gas to escape, right? So think about that in the terms of a soda, right? What's the best way to enjoy a highly carbonated soda? You want it to be cold, right? Because you want that CO2 to stay in there, and you want the pressure high, so you don't want to let it sit out open for very long. It'll become flat, all right? So low T and high P are ideal conditions for dissolving a gas, all right? And this can be quantified by a very simple equation given the name Henry's law. All right. So a very simple equation. What S gas is here is the solubility of the gas. KH, and I give it a lowercase k because I get my lowercase and uppercases confused quite often. So if you do it in cursive, that mitigates that problem. This is called Henry's law constant, and it's intrinsic to a specific gas at a specific temperature. All right, and then there's the P gas, which is the pressure of the gas. All right, so as of course we increase the pressure, we'd expect the solubility to increase, and that can easily be calculated, just a three-component equation. All right, so if you're given the pressure and you're given the Henry's law as constant, you can simply multiply them together to calculate the solubility. All right. The last solution I want to talk about are liquids dissolved in liquids. All right. So what we're talking about here is typically, two definitions. Something is miscible. And what this means is two liquids, a liquid is soluble in another liquid at any ratio. All right? So when we say something is miscible, that means you're not going to have a partition existing. All right, so two liquids that are miscible is the alcohol methanol and water. All right, so the alcohol methanol has the following Lewis structure. And water, of course, has this Lewis structure. So an old rule of thumb when it comes to solubility is likes dissolve likes. All right. So if we look at something that methanol and water have in common, it's this polar OH group, and water actually has two of them. In fact, the whole entire water molecule is an OH group, right? So methanol and water are miscible. That means you can add water and methanol all day long, and you're not going to see any separation. It's going to make a nice, pretty solution of water and methanol. All right. Now, on the other end, we have things that are called immiscible. And here we have a very small ratio of mixing of two liquids. All right, so these would essentially not mix. All right, they mix to a very, very small extent, but for the most part, they are not going to mix. All right, so two that come right to mind to me are water, if we look at its Lewis structure, and pentane, which I can draw the line angle formula. All right, so we have our 5 carbon, and if I want to draw the full Lewis structure, you can see why the line angles are nice to use, but nonetheless, we'll do this. 1 to go. Okay, and we look at pentane. All right, water and pentane are immiscible. All right, they are on total ends, opposite ends of the spectrum. All right, water is very polar. All right, it has the dipole. It has hydrogen bonding, an OH group. Pentane is what we call a hydrocarbon, or very greasy. All right, so it is completely hydrocarbon, so these guys would not mix. All right, in fact, a mixture, if you will, of water and pentane would look like this, where you would have pentane on top because it's less dense than water, and water on the bottom, and they would separate out into like an oil-water layer. All right, so that is the definition of a liquid being immiscible with another one. All right, and you can often tell by just looking at their Lewis structures or molecular structures whether they're going to mix or not. All right, so turns out that alcohols, all right, these are organic compounds. Right, they're organic molecules with an OH group. So if you're an organic molecule, it means you're carbon containing. All right, this is a very low-key definition. I'm not trying to get into this too deep here, but typically once you start getting over 5 carbon alcohols, become immiscible with water. All right, so there's a limit to how big your alcohol can get. All right, so if we look at water here, and we look at methanol, that OH group is not really hanging next to a very large hydrocarbon group. All right, however, if we go to pentanol, this would be pentanol. All right, it has 1, 2, 3, 4, 5 carbons, and has the OH group. This would be immiscible, and this guy would be mis. All right. So do you see why? All right. Now we have this very large hydrocarbon group, or this greasy group, that water is going to be quite repelled by. All right. So just looking at these molecular structures, if you see a lot of hydrocarbon material on a molecule, not likely going to dissolve in water, all right, or mix with water. All right, so that is the end of our discussion of solutions. The next video will wrap up chapter 11. We're going to go ahead and into colligative properties and colloids. Thank you.